Hi, I'm Arnel Ganello from Point Loma Nazarene University, and in this talk I'm going to talk about the mechanical energy aspects of baseball pitching. I'll give a quick overview on the pathomechanics of pitching-related injuries such as the elbow. Actually, I'm going to focus specifically on the elbow, and then discuss some of the ways that we measure and interpret energy flow during the baseball pitch using segmental and induced power analysis, and how we use these two approaches in the current research projects that we have going on at the lab, as well as with institutions with whom we are collaborating. So if you've been to San Diego, the campus of Point Loma Nazarene University is just north of Cabrillo Point. We moved into our current location, the lab, Biomechanics Lab, in 2018. The lab houses a state-of-the-art motion capture system, electromyography, force platforms, and that allows us to measure kinematics, kinetics, and muscle activation patterns of various human movement activities such as walking, running, jumping, powerlifting moves, and of course baseball pitching, which is my bread and butter. That's something, it's a research that I've been focusing on for the last, I would say, 15 years. And the system that we have is portable enough that we can bring into the bullpen and make the bullpen our own makeshift pitching lab and measure, kinematics and kinetics of various levels of baseball pitchers, from the Little League all the way up into the pros. We've also been fortunate enough to bring the system out to spring training in Arizona, where we work with a number of teams the last 5 years in collecting valuable data, biomechanical data, on these minor league and major league players. We also have a Modus baseball sleeve, allows us to estimate elbow valgus torque, Rapsoda system that we have access with our baseball team, and of course a team of young aspiring all-star biomechanists, many of whom have moved on and working in the field itself. I'm actually going to give a quick shout out here in a sec. So this is our system that's in the bullpen. We've got the motion capture system. This is a marker-based motion capture system that has special outdoor filter to block the sunlight and only focus on the reflective markers. There are 38 reflective markers on the pitcher, and they pick up the locations of those markers, the three-dimensional locations, and then using the software we can then estimate joint center as well as segmental definition, bone segments, and subsequently measure the kinematics and kinetics of the baseball pitch. In fact, I'm going to use this video to just kind of explain the various aspects, biomechanical aspects of the pitch throughout this video. So our research, we've been, very fortunate enough to present our research both on the international and national stages, not only, for me personally, but we've got a number of students and alumni who have presented baseball-related research at conferences such as the International Society of Biomechanics and Sports. There's a new conference held by the American Biomechanics and Baseball Society, as well as ACSM, which is the American College of Sports Medicine. So I'm going to highlight some of this research throughout this talk here. So a number of our alumni have moved on and currently working as a sports biomechanist. These are just a few of the institutions with whom we are collaborating. Wake Forest University, they've got a very nice pitching lab. In fact, I'll have some videos and images that I'd like to show you later in the talk. Cal Poly SLO, this is San Luis Obispo. We're doing a study together looking at the youth players and the relationship in anthropometrics and pitching mechanics, as well as CSU Sacramento. Driveline Baseball, they I want to say just hired, but they hired a couple of our alumni that are working as analysts and biomechanists there in their nice facility in the Pacific Northwest. Cedars-Sinai, the Carolyn Job Institute, they work with the Dodgers and the Angels and a number of different teams in the LA area. They have one of our alumni who runs the biomechanics lab. And then I'm sure many of you are familiar with Glenn Fleisig, Dr. Glenn Fleisig at the American Sports Medicine Institute, with whom we've been able to collaborate on a number of projects over the years. And of course, in Major League Baseball, especially in the last, I would say, 4 or 5 years. A number of these organizations have been more receptive to the science of biomechanics and welcoming the technology and the science to do a couple things, right? They're trying to minimize the risk of injuries in their players as well as their performance on the mound or field if we're talking about, position players. So a lot of these organizations, have reached out to, different biomechanists in academia, and a lot of them have ended up hiring. In fact, we've got 5 alumni who are working with different organizations right now as a sports biomechanist. So a quick shout out to all the PLNU alumni here. So in addition to being a biomechanist, I'm also an athletic trainer. And as an AT, the health and injury risk of all the athletes that I work with are obviously a top priority. So we use biomechanics in order to understand the pathomechanics and etiology of these injuries, specifically in baseball, which we know the majority of which are pitching-related injuries. Specifically, pitching-related elbow injuries remains the most prevalent injury that we see in baseball at all levels of the sport. In fact, at the pro levels, the majority of those who are on the DL are pitchers with elbow injuries. There is a study out of NYU and using the sports or Major League Baseball's injury surveillance system, they found that 43% of major league players and 33% of minor league players sustained an elbow injury severe enough to require surgery. These are all pitchers, by the way, baseball pitchers. At the collegiate level, the number is not that great as well. Collegiate pitchers are nearly twice as likely to sustain an elbow injury than any other position. At the high school level, nearly 60% of all baseball elbow injury are pitching related, and even at the Little League and Pony League levels, 18 to 29% of youth players develop some kind of elbow pain or related symptoms. And these injuries, the risk of these injuries related to a repetitive exposure to what's known as a valgus torque. And the reason why I like to focus on the elbow is because the injury etiology that I'm going to explain here in a sec can be used to explain the etiology for shoulder injuries as well. So here is a player that is in what's called the late arm cocking phase. This is as the glenohumeral joint of the throwing arm approaches its maximum external rotated position. And if I were to measure that out, we're close to 160, maybe 170 degrees of external rotation. As it approaches that position, the load that's on the shoulder, what we call an internal rotation torque, increases, while simultaneously at the elbow, that same torque places the elbow in what's called a valgus load or a valgus position. And so that repetitive exposure to those high valgus torque is what's known to lead to a higher risk of an elbow injury. And when we look at a valgus torque, what's happening internally at the elbow is the medial structures here, as I show, goes under an extreme amount of tension, and while the lateral structures go in an extreme amount of compression. We call that a force couple. And so those structures represent or facilitate what's known as a varus resistance. That is the resistance to that external valgus torque that I just described. And according to cadaveric research, I would say more than half of that varus resistance is made up by the ulnar collateral ligament, specifically the anterior band of the UCL, hence Tommy John. This is the most common pitching related elbow injury, which I'm sure many of you are familiar with. There's also some research to suggest that the musculature around it also assists in that varus resistance. This is the muscles of the flexor pronator mass, the FPM. There's also osseous contributions due to the articulation between the capitellum and the radial head, and we find some issues with younger players with throwers elbow and osteochondritis dissecans and things like that. And again, that's all related to that same etiology, that repetitive exposure to valgus torque. And what we know through these biomechanical analysis is that equates to a certain amount of mechanical energy being absorbed by the elbow as the arm transitions from the late arm cocking phase to the arm acceleration phase. And we know that that joint is the weakest link in the kinetic chain. Now, when I'm talking about mechanical energy, if you've taken physics before, that is just simply energy that is due to motion, energy that's due to mechanics. So these are things like potential energy, or mainly gravitational potential energy. Kinetic energy was the energy of movement, rotational energy, and there's energy due to reaction forces at the joints. So I'm not going to go into the weeds with all that, but there are ways at which we can measure mechanical energy throughout the kinetic chain. And with the kinetic chain, and if you've heard that term before, there are different descriptions and definition of what the kinetic chain is. But if we look at pitching and just throwing in general, it is a classic what's called an open kinetic chain. It's open because the distal end is free to move, right? You're throwing an implement, and a player is able to throw that implement as fast as possible or as far as possible by coordinating all the various segments of the body within the kinetic chain in this case, what's known as a proximal to distal fashion. So the way that we can break this down is by looking at the various phases in the pitching motion. So I've got here the stride phase, which is defined from the wind-up, or really the max knee height to front foot contact, and then from front foot contact to the maximum external rotative position of the shoulder is known as the arm cocking phase, which I alluded to that phase earlier. And then followed by the acceleration phase. This is when the throwing shoulder reaches its maximum internal rotational velocity into ball release. And what I show you down here, if we take that pitching motion, normalize the pitching motion between front foot contact, 0%, to ball release, 100%, we can then compare pitchers who have different pitch times and whatnot, and then look at the timing in which the angular velocities of the various segments of the body move. And when I talk about angular velocity, I'm talking about rotational angular velocity. This is what's known as transverse angular motion. Coaches like to call that opening up towards home plate. So what we see here is when that action, that angular velocity of the specific segment is occurring. So in the stride phase, we know, just based on what we see, what we observe both in the lab as well as just on the field, that the pelvis is rotating or opening up first, right? Followed by the trunk. You can see here, there's trunk rotation throughout the arm cocking phase and into acceleration, and then shoulder external and then internal rotation. And what's key here is that while the trunk is opening up, towards home plate in this case, the shoulder is externally rotating in the arm cocking phase until it reaches its maximum position, and then of course in acceleration phase it internally rotates into ball release. That is also coupled by elbow extension here. It extends. In fact, I'll show you a graph here and how that looks, and then ultimate flexion during the acceleration phase here. So this is an example of how that angular velocity looks in the transverse plane for those various segments. And we could break it down with a number of different segments, but I'd like to focus and keep it simple on the pelvis, followed by the trunk, followed by the elbow, and followed by the shoulder. Now, there are a couple things that we point out here. This is one of the graphs that we typically show our baseball players when they come in and want to get analyzed, biomechanically analyzed. Is we'll give them these numbers. These are the peak angular velocities for the pelvis, trunk, elbow, and shoulder, or specifically the glenohumeral joint, as compared to norm reference standards. And this is a sample of adult players, meaning collegiate players. Now, I always tell these pitchers, I go, don't get too hung up on the actual magnitude. You see that, why am I only 4,000, or why am I only 2,000? And go, look, that only tells you half the story. Remember, this is angular velocity, and so studies have actually shown that high school players actually have faster angular velocities at the shoulder than collegiate players, yet they're throwing, maybe 10 miles per hour slower. And it's because of angular momentum. Angular velocity only makes half of a part of that equation, and that's because of mass, right? Differences in mass properties that are apparent in high school, collegiate, ultimately to the pros. So what I always tell players and coaches, okay, just focus on the timing. I think many coaches are familiar with the kinematic sequence in which these segments, and we're looking at the peaks in which these occur, pelvis, trunk, elbow, and shoulder. And what we see here, and I know this doesn't really follow the proximal to distal sequence, but for the most part, for all intents and purposes, the peaks of the elbow extension velocity and the shoulder internal rotation velocity occur right about the same time. You're talking just a few milliseconds right here, and a lot of it has to do what the shoulder is doing in internally rotation during acceleration phase, where the elbow peaks at extension, and then obviously goes into flexion from there. So we focused mainly on timing. In fact, when we just focus on timing, we can then plot out just those times in those specific segments or joints with respect to a 95 confidence interval for that same sample. So this is timing in which the peak pelvic angle velocity occurs, trunk, followed by the elbow, and followed by the shoulder. This is in the same normalized pitching motion time, 0% to 100% there. So if we take picture A here, and one of the things we're showing, it looks like you are peaking in your pelvis angle velocity before front foot contact. Whereas what we see in the among normal, 95% confidence interval shows here, that's right around, 20-30% in the pitching motion. It's okay that the pelvis rotates before frontal contact. That's okay. But in terms of when it actually peaks, what we want to see ideally, at least according to the summation of speed principle, and if you're familiar with that principle, this is a principle that was first reported by Carol Putnam in that group in Berkeley, where it postulates that the motion of a segment will initiate, the segment will initiate its rotation when the segment proximal to it reaches its maximum angular velocity, so that it picks up, in other words, takes that energy up from the pelvis to the trunk and ultimately to the throwing arm. And so in this case, this picture is able to follow that. You can see here that the trunk peak angle velocity, this is rotational velocity in the transverse plane, it's late. It comes in after the pelvis. That's what we want to see. And I did a study a couple of years ago where it showed that high school players in general, these are players who are, just starting out and starting learning how to get the hang of it throwing off the mound, tend to rotate their trunks too early. And some of them have a peak trunk angle velocity that occurs before the pelvis reaches its peak angle velocity. So that's not a good kinematic sequence. So we like to show this just to kind of give an idea of what's happening throughout the pitching motion. So then if we extended that analysis and look at the flow of energy through the various phases. So this is the same timeline that I showed you here. That I showed you earlier with the stride phase, the arm cocking phase, and acceleration phase. And the first thing we see, as I mentioned earlier, into front foot contact is that pelvic rotation. And what's happening here in the stride phase, and I definitely want to emphasize what's going on with the legs is, of course, the legs are responsible for initiating the linear acceleration towards home plate. But what's happening here is as it goes from, the wind up at the max knee height into front foot contact, remember the pelvis is already rotating. So its job, the leg's job in this case, is to provide that stability, provide that foundation on which the pelvis can continue its rotation, because it's generating power, it's generating that energy flow that ultimately transfers over to the trunk. And while the trunk is rotating, it's also generating mechanical energy. The shoulder is externally rotating. That is that natural angular momentum as the trunk opens up and the shoulder, as I mentioned earlier, externally rotates. It is also absorbing energy along with the elbow, and then ultimately in acceleration, there's power that's generating in order to release that energy to the ball. So we use what's known as a segmental power analysis to understand the exchange of energy from one segment to the next. So it measures three aspects of energy flow. One is energy generation. How much does a torque generate energy at a segment? Another one is energy absorption, as shown you here for shoulder external rotation, how much of that energy is being absorbed by that segment. And of course, transfer, how much of that energy is being transferred. Okay, now let's take a look at how this energy flows throughout the kinetic chain during the baseball pitch. So I have here an animation that I built in what's called Visual 3D. And what I did here is I color-coded each one of these segments based on whether or not they are generating energy as indicated by red or absorbing energy as indicated by green here. And if we just focus real quickly just on the legs, take a look at the stride leg. Stride leg is the front leg as it contacts the mound. Here, let me go ahead and see if I can fast forward a little bit. So it's accelerating towards the front of the mound as the player should. And then here, this is when, there we go, that's front foot contact. Notice it's turning green. That means that leg is absorbing energy. That is controlled knee flexion. In biomechanics, we call it a shock absorption. Right? There is absorption here that's happening due to eccentric contraction of the muscles around the knee as well as the hip in order to stabilize the foundation on which the pelvis can then rotate or continue its rotation towards home plate. This is very important because you often hear of how the kinetic chain starts with the legs and moves up the pelvis, the trunk, and ultimately to the throwing arm. That is only partially true, because really the generation of power comes from the core, from the pelvis and the trunk, and ultimately to the throwing arm. The legs are there. They do not transfer any energy, at least according to the data that we've seen and those reported by others. There really is no energy being transferred from the legs to the pelvis region. What we're seeing is happening though, and again, I don't want to diminish the role that the lower body segments, the legs, do during the baseball pitch. Its job is to help facilitate pelvic rotation, and ultimately that leads to the core rotation, provides that foundation on which that rotation can occur, and that leg brace, as some coaches like to call it, equates to a certain amount of shock absorption, a certain amount of eccentric contraction. So that's what we see here, energy absorption. And take a look at the pelvis. The pelvis is red. So that means it's generating power. It's generating energy that ultimately transfers to the torso and then to the throwing arm. So that is how, at least using this technique, we are able to measure the flow of energy from segment to segment using segmental power. Now, this by no means is a novel technique. Segmental power analysis has been used for years, if not decades, for a number of different human movement activities. But in just baseball pitching alone, there are some research that was published out of Japan that uses segmental power analysis to measure mechanical energy flow during overarm throwing and baseball pitching off a mound. More recently, out of Harvard, they took a look at overarm throwing and determine or estimate mechanical work and mechanical power for the torso, the shoulder, the elbow, and wrist. But the problem or the limitation with a segmental power is that it only addresses the flow of energy between adjacent segments, like, for example, pelvis to trunk or trunk to the throwing arm. It does not measure the contribution that an anatomical distant segment has on, say, for example, the throwing arm or the baseball pitch. The baseball itself. And we know, as I mentioned earlier, that baseball pitching is a classic open kinetic chain motion that involves multi-articular body motion. It acts much like a whip, so that the energy that's generated here in the legs, the pelvis and torso, which I mentioned earlier, is the main source of power for the pitch itself, transfers and moves up the kinetic chain ultimately to the distal end of the throwing arm. So that's much like a whip, right? If you were to, swing a whip or whip a whip, if you will, and that energy from the hands will flow down that rope. Very similarly, that happens with a baseball pitch. The problem is with segmental power analysis, it doesn't address what that effects are. So we have to find another way to analyze that. And one of the ways that we've done, and others have done this as well, to see, okay, what are the contributions of, say, the pelvis and trunk towards the ball velocity, or if we're measuring injury risk, elbow valgus torque, is the use of statistics using regression. So this is one study we published over a year ago now, where we looked at the contributions of mechanical power at the core, this is the pelvis and trunk, in determining or predicting ball velocity, and in this case elbow valgus torque. And we found that trunk rotational power was a significant predictor of those two metrics. So this, as you know, is a metric of pitching performance with ball velocity and injury risk with elbow valgus torque. Similarly, this is Jacob Hauenstein's study out of Marquette and St. Louis University. They found that the power that's due to what's called, the power is due to torques and forces, and the joint force due to pelvis and trunk, and the segmental torque due to the trunk in terms of power were significant predictors of, in this case, the ball velocity in their, they had youth players, so these are younger players. So very similar situation here, but as I mentioned earlier, the reason why we have to use, these predictive methods, these regression methods, is because a segmental power analysis does not address the contributions of anatomical distance segments to the distal segment. So another technique that we use more recently is what's known as an induced power analysis, which is largely based on an induced acceleration analysis. And this is a study that I and my colleague, Dr. Rafael Escamilla out of Sacramento, published earlier last year. And what an induced power analysis is largely based on is, as I mentioned earlier, an induced acceleration. So if we take this system here, this is a system of 3 linked segments, and each one of these segments are connected by a frictionless point, and the only source of torque is, some lever here, or some, just assume it's like a muscle here. Well, that torque, T, will not only accelerate the segment to which it is directly attached, but we know that will also accelerate the other segments, even those specific segments do not have any sources of torque or forces. Well, it turns out quantitatively we can model what that induced acceleration here using this, what's known as the state space equation. Don't get too hung up on this equation here. But what the effects are of T, of torque, is due to what's known as a velocity dependent torque. It's called velocity dependent because it's dependent on motion or the effects of what the torque is doing at, just call it segment A. And those are the Coriolis and centripetal effects. Again, if you remember physics, anything that is rotating has these Coriolis or centripetal effects, especially if it's accelerating. So it turns out that we can measure that. You can measure it in 3 dimensions, and this is how we use it. This is the equation. There's also contributions from gravity. We found that that was negligible. So in all of our analysis, we ignore the contributions of the gravitational vector. IPA, or induced power analysis, has been used to describe the induced power or induced accelerations of the center of mass, for example, or the trunk that's due to ankle plantar flexors, or due to knee flexors or knee extensors during cycling, for example, or during walking. This is a study out of Stanford where they looked at the contribution of ankle plantar flexors on the acceleration of the center of mass during walking using an induced or a version of an induced power analysis. And then looking at soccer, just during a soccer kick, and this is out of Japan, where they used an induced acceleration / power analysis to understand the contribution the trunk has in swinging the kicking leg forward, and we're able to measure that contribution. So it allows us, an IPA allows us to decompose the induced power. In this case, we're talking about pitching of the forearm that's due to the movements of the other parts in the kinetic chain. So this is the study that I just showed you. That was published a year ago. It's a fairly simple model in that it's only 10 degrees of freedom. 10 degrees of freedom is just sources of rotation. So if we take rotation, 3 rotations at the trunk, 3 rotations at the shoulder, 2 at the elbow, and 2 at the wrist, that is a total of 10 degrees of freedom for that system. Based on the 10 degrees of freedom system, we can then decompose the induced power at the throwing arm, more distal throwing arm, this is more specifically the forearm, based on this governing equation. Again, you can ignore the equation itself. What we're trying to measure is the effects of these various decomposed components on the induced power of the forearm. Okay, so once we are able to calculate the induced power, we can then integrate between the intervals of front foot contact and maximum elbow valgus torque. We chose that interval because we were interested on the contributions towards injury risk at the elbow. So by integrating the power, we get what's called mechanical work, or the change in kinetic energy. And we can then see, okay, where are the culprits? Where are the ones that are contributing to the induced power at the forearm? So this is how it looks. If we were to graph it out throughout the pitching motion, this is just one example of a representative pitch. As I mentioned earlier, the way these degrees of freedom are labeled, R1, R2, and R3 represents trunk flexion extension, trunk lateral tilt, trunk rotation. Whereas R4, R5, R6 represents the shoulder. So this is flexion extension, abduction, adduction, internal, external rotation, followed by the elbow. That's flexion extension, varus valgus. And then finally looking at the wrist, which is flexion extension and ulnar and radial deviation. So this is the induced power that's due to the velocity dependent torque. Remember, this is the Coriolis and centripetal effects of these components. And what we found is, as expected, that the biggest contribution to that induced power due to velocity torque is due to trunk rotation, due to trunk motion. So that is the interactive effects of trunk motion. Why is this important? Because back up to the segmental power analysis studies that I showed you, we found that trunk rotation power was a significant predictor of ball velocity, as well as a significant predictor of elbow valgus load, but that was only found using regression, right? That only gives you the percentage of variance that can be explained by these components. That's not really a direct cause and effect relationship. That, as you know, correlation does not equate to causation. This, however, gives us those direct contributions. And I say that with a little caveat because the direct muscular contribution is actually minimal. Its direct effect is manifested by this velocity-dependent torque. That's that whip-like effect. That's where if I were to move my pelvis, that's going to move like a wave up my body and ultimately to the throwing arm. Okay, so what does this really mean in the context of whole body mechanics during the baseball pitch? So this is the same video I showed you earlier, and if we concentrate on what the pelvis and trunk is doing during the baseball pitch itself, in terms of energy, I just told you that the major components, or the primary component of the velocity dependent torque, this is the induced power at the elbow at the throwing arm, is due to trunk motion. And look at late arm cocking phase here, right around there. Okay, I kind of missed it, but notice that the shoulder maximally externally rotates at right around 180 degrees. And for most players, they're only able to get to that peak rotation when they're throwing. That is that whip-like effect. That's that energy. That's the interactive effects of pelvic and trunk rotation during the baseball pitch itself. You ask any player and ask them actively, hey, go ahead and externally rotate your shoulder. They can probably go back maybe 120, 130 degrees of external rotation. And maybe passively you as a trainer or as a PT be able to do that. But to be able to get to this position, they're only able to do that during the baseball pitch itself. It's because of that energy. That's the interactive effects. That's the Coriolis and centripetal effects of pelvic and trunk rotation. This is why I emphasize core musculature and strengthening and timing, because ultimately that is the source of power that a pitcher has. Again, legs are important. They provide the foundation and stability, but there's really not much energy being transferred to the pelvis. And I'll actually I have some data to illustrate that. So in this particular study that I just showed you, this is the mechanical energy, mechanical work that is due to those various components of the induced power of the forearm. And I can show you here that the components of that induced power is due to mainly trunk motion, due to trunk flexion, that's trunk forward tilt, and trunk rotation. And it's negative because why? Remember what I told you during the arm cocking phase? There is absorption at the forearm, at the elbow, right? That's what we see. We see that there's energy being absorbed by the structures of the elbow. And what are the clinical implications of that? Well, that's about UCL. I talked about the various injury etiologies of the elbow itself, both on the lateral and medial side of the elbow. So in summary, for this specific study, we found that the velocity-dependent torque represents roughly 61% of the induced power at the elbow. The rest of it was all musculature or power that is due to muscular torque at the shoulder, for example, which is obviously important. But more than half of that motion, or of the induced power at the forearm, is due to that whip-like effect, due to those velocity-dependent effects. So using this decomposition, induced power analysis, we were able to determine that the largest contribution in the late arm cocking phase for the maximum elbow valgus torque was due to those trunk flexion and rotational components of the velocity-dependent torque. In this particular study, we were interested in injury risk at the elbow, so hence we were looking at MEV. So this reinforced findings that I mentioned earlier that suggest that trunk motion plays a critical role in elbow valgus loading and subsequently potential injury risk. It somewhat belabors a point that we already know. However, it reinforces it from an energetic perspective. Now, limitations of this approach, at least in the model that we used, is that we mentioned that there's energy absorption that is occurring at the elbow, at the forearm. However, the model does not quantify the specific energy absorption at those structures, at the UCL or at the FPM. There are some studies, as I mentioned earlier, Roach and Lieberman out of Harvard. They postulated that energy stored, what we call elastic energy, is being stored during the late arm cocking phase and then release, kind of like a rubber band, during arm acceleration. Theoretically, it makes sense, but no one has been able to quantify that yet. Now, Jimmy Buffy and his group out of Northwestern, and Jimmy has now, well, he moved to the Dodgers organization and now has his own organization. He was able to model the different soft tissue structures at the elbow using some forward dynamic simulations, and found that the flexor pronator mass represented a significant amount of contribution towards that very resistance. And so if we were able to take those model assumptions and maybe build that into what we have here in IPA, we may be able to quantify what that storage is, if any. If there's any differences in storage, elastic storage, during the late arm cocking phase, and then how much of that is released during the acceleration phase itself. That would have significant clinical implications for both injury, as I showed you here, as well as pitching performance using ball velocity. Now, another limitation of this particular implementation of the model is, as I showed you earlier, it was only upper body, right? We're looking at pelvis, trunk, and the throwing arm. It did not look at the contributions of the lower body segments of the legs themselves. And the major reason why is that at the time of data collection, we didn't have force platforms embedded in our pitching mount. And you need force platforms in order to measure three-dimensional ground reaction force data in order to accurately model the kinetics in the lower body, in the legs themselves. So we've now partnered up with Wake Forest and their pitching lab. This is a couple of images from their lab at Wake Forest in North Carolina, which is adjacent to their bullpen in their baseball field. And this Pro mounts, I believe it's Perfect mounts that makes this types of mount, is instrumented. So it has 3 force platforms by AIM-TI, 1 by the rubber and 2 down the mount itself. So we could measure ground reaction force data throughout the pitching motion and use that information along with the marker data to give us a full body, three-dimensional biomechanical analysis of baseball pitching, and subsequently an energy flow analysis using induced power. So some of the early work we've done already, this is exciting work that we've done in the last year. We presented in this data in part at last year's American Society of Biomechanics meeting. So I'm just going to show you a couple of examples of that data. So this is induced acceleration of the throwing arm. We're looking now at ball velocity. What are the contributions of everything, all the major segments in the kinetic change to ball velocity? And remember what I mentioned earlier. Look at this. This is lower extremity. These are the legs. It is, I don't know if you guys can see this, but this is kind of in the pinkish curve, very minimal. That means the lower extremities have a minimal direct contribution to ball velocity. And even with the pelvis, look at that. That's the waist. And you're thinking, what did I just talk about for the last 20 minutes? I said the pelvis and trunk were important factors in determining ball velocity during the baseball pitch. Let me fast forward a little bit. This is the shoulder. This is the induced acceleration component due to shoulder rotation as expected, but this is the velocity-dependent torque. The contribution of pelvis and trunk rotation, as I mentioned earlier, is manifested, in this case, in the induced acceleration of the forearm through this velocity-dependent torque. That's what we see here in the red. And notice that it kind of aligns with what we see at the shoulder. Remember, this is acceleration. So that lends, I should say, more evidence to reinforce the notion that there is a certain amount of release of energy as the arm is transitioning from the arm cocking pace into arm acceleration. And so if we were to integrate the induced acceleration, we can then break down the induced velocity of the throwing arm. So as expected, we see here that the shoulder here, as well as the velocity-dependent torque, represents the largest contribution to the induced velocity of the distal end. And again, look at the lower extremity. Remember, the lower extremity provides the foundation on which rotations of the pelvis, followed by the trunk, can occur. Take-home message here is that the power comes from that core, and the timing, and we can talk about strengthening. I haven't had any data yet on the effects of different training interventions on how this energy flow is manifested during the pitch. However, I think one would surmise that those interventions would make a difference on how well that energy flows up to the throwing arm using this approach. So, I'm very excited on the research that's coming up the pipeline, if you will, with the technology, with markless technology and hybrid systems are coming out. We can get a full picture from an energy flow perspective of what these baseball players, these pitchers are doing at different levels, high school, collegiate to the pros, as well as compare different training interventions to, one, improve their performance, and number two, lower their risk of injury. I want to take this opportunity to thank all my grad students who have helped over the years. This is just pictures of us going to spring training at different points in time in Arizona. So I just want to send a quick shout out to PLNU MS Chem. Thank you.